The final thing I want to do as far as Cauchy-Riemann equations go is to do some examples. So I've said all the statements I want to say, but let's think about some examples and let's look at the function. So let's start with z cubed. So this is one that the book does, but I want to do it anyway, so I think it's a good example. So let's look at f of z as z cubed. So we're going to think of z as x plus iy. And therefore f of xy is going to be x plus iy quantity cubed. And that's going to turn out to be x cubed plus 3x squared times iy plus 3x iy squared plus iy cubed. And so this is going to turn out to be, let's see, x cubed minus 3xy squared plus I times 3x squared y minus y cubed. Because I cubed is minus I. So you factor out the I and you still have a minus for that y cubed. So this is f of xy. And then our u is going to be this first part, x cubed minus 3xy squared. That's our u of xy. And likewise, our v of xy is that quantity 3x squared y minus y cubed. Okay, and so let's just verify that this function is differentiable everywhere by looking at the Cauchy-Riemann equations. So if we look at u sub x, what's the partial of u with respect to x? Well, that's going to be 3x squared minus 3y squared. And if we look at the partial of v with respect to y, that should be the same thing. And it is indeed 3x squared minus 3y squared. And if we look at the partial of v with respect to y, the x cubed goes away. You end up with, let's see, negative 6xy. And if you look at the partial of v with respect to x, you're going to end up with 6xy. And the y cubed differentiates to 0. And so you really do end up with what you want. U sub x and v sub y are equal. U sub y and v sub x are equal, except for that minus sign. Okay, so one's equal to negative the other. So these really do satisfy the Cauchy-Riemann equations. But also let's look at u sub xx, u sub yy, and so on. So if we look at the second partial of u with respect to x, that's going to end up being 6x. And if we look at the second partial of u with respect to y, that's going to be, we're going to look at u sub y and differentiate with respect to y. We'll get negative 6x. And indeed, this tells you that the function u is harmonic. And in fact, it's harmonic over the entire complex plane, because no matter what point you plug in, you're going to get 0. Okay, so that's true for all values, for all complex numbers. And then I'll let you verify that this is true for v as well. Okay, but that's the story there. One last example. Let's look at the function e to the z. Again, z is x plus iy. And so e to the z, if we're thinking about it as a function of x and y, is going to be e to the x times cosine of y plus I sine of y, right? We know what this is, e to the x plus iy. We've seen this before. So this tells you that f of xy is going to be e to the x cosine of y plus I times e to the x sine of y. And so if we look at the partial of f with respect to x, if we look at the partial of u with respect to x, so u is the first part, then that derivative is going to be e to the x cosine y. If we look at the partial of v with respect to y, that's going to be, if we differentiate this term with respect to y, so the sine of y is going to become cosine of y. E to the x is a constant, and those are indeed equal, so that's good. And then u sub y is going to be equal to, let's see, if we take u and differentiate with respect to y, we'll get minus e to the x sine of y. And then finally, what are we missing? V sub x. If we take v and differentiate with respect to x, we're going to get e to the x sine of y. Okay, and then exactly like we want, we get that u sub x equals v sub y, and u sub y equals minus v sub x. So these really do satisfy the differential, the Cauchy-Riemann equations, and therefore f is differentiable everywhere. Finally, let's look at the harmonicity of the real and the imaginary parts, and we'll just do one of these again. But if we look at the partial of u with respect to x, where we differentiate twice, then what we're going to get is e to the x times cosine of y. Because we're just differentiating e to the x, that's itself. Cosine of y is a constant. And if we look at the partial of u with respect to y, the second partial of u with respect to y, what we're going to do is we're going to take the partial of u with respect to y and differentiate again with respect to y. So this will be minus e to the x cosine of y. And that's exactly what we want in order to get that u is harmonic over its domain, which it is, because the second partial of x plus the second partial of y are going to add up to be 0. And again, likewise, this also is true for v. I'll let you verify that on your own time.